Hi, everyone. This is Liu Yang from the Applied Math Department. He's going to be giving a talk on physics-informed neural networks, so it should be very interesting. And go ahead.
Yeah, okay, thank you for inviting me. Thank you for the introduction. So, it's more like a very basic tutorial introduction, instead of like advanced advanced research problems. Anyway, so basically, I will first introduce the physics-informed neural networks, and in specific in for and inverse problems, and then I will have introduce the application in a fluid mechanics problem, and then I will introduce Bayesian physics-informed neural networks. So basically, it's for uncertainty quantification. So we talk about uncertainty quantification. Actually, there are other uncertainties. But Bayesian physics-informed neural networks are only for tackling the aleatoric and epistemic uncertainty, which arises from, so basically aleatoric just means the data is noisy, and epistemic basically means data is gappy, or where you don't have infinite data, you only have finite data. So that will also have some uncertainty. There are also other uncertainties, for example, the physics system itself is stochastic, or the model is not cannot perfectly match the real world. So there's model uncertainty, but that is not covered by this framework. So Bayesian framework is just only for data uncertainty. And I will show that the Bayesian physics-informed neural network with the Hamiltonian Monte Carlo posterior sampling can provide meaningful uncertainty. And it's more robust than vanilla PIN for noisy data. And lastly, we will discuss the prior of the Bayesian PINs. Okay, let's go to the first section. So this is actually a schematic of PINs. So the spirit is that we will employ two or more neural networks that share the same parameter to represent different terms in the neural network. So so firstly, we will use a neural network to represent for example, the solution U. Well, it's just represent that. We have to go to the training now. The input is going to be the spatial coordinate and time coordinate, the x and t. This is just like a neural network with the parameters w and b, and output is the u at x and t. Okay. Of course, we can have a identical operator. So basically, this all. And then we can also calculate the absolute value. Okay, that's the interesting part is that we can also calculate a derivative analytically by auto differentiation. So that's actually the key. This is totally different from traditional classic numerical methods like finding difference, finding volume, because there you will calculate the derivative using numerical scheme. But now we are using auto differentiation. Well, maybe I should give a quick introduction of auto differentiation. Basically, because we have analytical expression of the neural networks, then we can use chain rule to calculate the derivative. So auto differentiation just another word of chain rule, I should say. And then we can calculate f. Looks like this. And well, we assume that the equation looks like this. So f should be 0, and then we can build a loss using the boundary and the initial condition and the boundary condition of u, and the equation, this part should be 0, right? So the loss is looks like this. So this is the loss function where lambda u and lambda f is just two weights. And the first term is the initial and boundary condition. You can see that it's basically the mean squared error, and the second part is the residual loss is also mean squared error. Does it make sense? Okay. Yeah. So basically this is just the initial data for the initial condition and boundary condition, and this is t ui and x ui, just where data are located. Okay. And then take this for example. So this is showing forward problem. We'll solve this equation. And here the crosses are where the data are located. So we know that here boundary is 0, and this is boundary, this is 0, and here we have this, just some samples, and then we can just using what I've just introduced in the last slide. So we'll get this. So you can see that the prediction matches the exactly perfectly, even for this kind of discontinuity. We know that like using like, I mean, if I want like if we use traditional numerical methods, the discontinuity is actually a big problem. We will have like oscillation, etc. I mean, but neural network they tackle this kind of problem very like perfectly. And here we show the pseudocode, I should say, but it's more than like it's actually pretty like really simple. I mean, you use TensorFlow to kind of the gradient, it's just like one line, like TF dot gradient, super easy.
Oh, can I ask a quick question here?
Yeah.
It looks like you only have data points on the boundary of this box. Is the neural network able to learn the solution within the boundary as well?
No. It will learn the whole domain, the solution on the whole domain. And here we show the solution on three time snapshots. So
yeah, basically, the training data is only on the boundary. Yeah,
training data is on the boundary and the initial condition. But you also have PDE, right? The PDE, you told him you told the neural network the PDE, so you can solve the PDE. Well, if you solve this equation, you only need boundary condition and initial condition.
Awesome, thank you.
Yeah. I mean, this crosses as data, but we can solve the equation on the whole domain. That's it. It's not like it's different from like just do a regression. I mean, without the PD, you can never know the solution inside the domain, right? Okay. And then we go to the inverse problem. Or like a PD discovery. Well, this is also like a simple problem. The point is we want to infer lambda 1 and lambda 2, but of course we need some data in the interior of the domain. So in specific, we assume that we know data here and here. So here are the data. We don't even know the boundary condition and initial condition. Okay, we just know this data. So and here. So basically, to infer the lambda 1 and lambda 2, we only need to like set lambda 1 and lambda 2 both as trainable variables. So they are also like part of the training, and then we can just do exactly what we did. I mean, in the forward problem, and then we can get lambda 1, lambda 2, and here is the result. So with clean data, which means noiseless data, you can I think basically you can match the exact solution perfectly, but with some 1% noise, you can still like to have a decent result. But I mean, okay, this work is not done by me. This is like this is done by another postdoc. But he didn't in the paper he didn't show the like, for example, more noise that if the data noise size is larger. But well, my experience is that if you have like a 10% noise, you need some additional technique, for example, regularization, or well, maybe better use the Bayesian PINNs, as I will introduce later.
Sorry, can I ask a question here in the previous plot?
Sure.
Yeah, here. So your network for your lambda 1 and lambda 2, there are like two neural networks themselves, right?
Oh, sorry, I didn't make it clear. It's just like a trainable variable. It's just like a variable. It's not neural network at all, because there's no. It's just like it's just a number, real number, right? You don't need to like have a neural network to predict number 1, number 2. It's just two numbers.
Okay, so they are variables, but they're the simplest neural net, just one neuron, right? That you want to figure out what's the value for.
Yeah, you can do that. You can say that. Yeah.
Yeah, because the reason because if it's an inverse problem, you don't know in advance that lambda 1 and lambda 2 have simple forms, right? So you have to assume like a general function and try to.
Okay, so that's a good question. So basically, in here, I mean, this is just a toy problem. We just assume that, well, this is like
okay.
It's just a simple constant. But I mean, yes, you are right. It can be like dependent on x and t, or even dependent on u. And then you can use the neural network to present that. That's exactly what we did in the in other papers. I mean,
Okay.
we have this kind of example in other papers. Here we just did show that. Maybe we will not show that today, but I mean, you can take the spirit, right? It's just like understandable.
Yeah, makes sense. Thank you.
Yeah. Okay, and then this is like more like I think it's a little bit more complicated. It's like a 2D. It's like 2D fluid mechanics problem. Well, I mean 2D in X, and also we have a time dependence. And okay, so basically we have the data in this like interesting domain. Interesting domain. And in specific, I consider two cases of data. Like square is like we have like kind of big data, and the star is like we have not too many data. And the data, we know that the data is only on C. Honestly, I don't know what to see. It's just like it's just like a term in the Navier-Stokes equation. Oh, it's like concentration, but honestly, I still don't know what is concentration. And then we use a neural network to we take the t and x, y as input and output the c, u, v, p. So c is the concentration, u is u and v are the velocity, and p is the pressure. And then we have we get the, so we just input the Navier-Stokes equation. So we get 4 terms because they are like four equations, and then we get like the loss function. Loss function consists of well, this is the data, right? So this is just the data loss, and the rest is just the residual. Wait, that's for anyway. And okay, this is just here we just show the regressed term and the reference term. We can see that, well, they match kind of well. But okay, maybe this figure is like more interesting. So basically, we have, so let me explain. So here, so this here is show like how many data on X we have, and how here we show like how many snapshots in time we have. So basically, like, okay, here for example, the square just means we have 15,000 data on X and 201 time snapshots. And star just means like we have 500 data on X, well, on X and Y, I should say, and in space actually, and 13 time snapshots. And here we show the relative L2 error of C, U, V, and P. You can see that, well, in this region, well, you can actually fit the concentration perfectly. Obviously, it's like 10 to the I think it's like 10 to the -2 or 1% relative error. As for the velocity, pressure, and velocity and pressure is like a 10% error, which is still like kind of good. But if you have like you don't have enough data, then the error gonna be huge. By the way, later our group also like try to have some results on just, I mean, here we just use the simulation data, but later we also use the experimental data, just like observe the concentration, etc., to solve the velocity field. But that is not published, I think. But yeah. Okay,
Liu,
now
I have one more question, Liu.
Yeah.
So here, when you're optimizing,
sure.
Yeah, when you're optimizing the neural net, when you're trying to minimize the loss in the training set, are you training on both the variables C, U, V, and P, as well as the mean square error, or are you training only on the mean square error?
Oh, so basically we only have data on C. So basically, this term is the data loss, but we don't have data on U, V, and P. So that is that is something you don't know.
So when you're optimizing it, are you optimizing it just based on reducing the mean square error, or are you optimizing both C and the mean square error at the same time?
You optimize the data error, which is for C, and also the PD error or residual error simultaneously, because they are just summed together and then calculate the loss.
I see. Awesome. Thank you.
Yeah. Thank you. And then go to the Bayesian stuff. So basically, I would say Bayesian PINNs is just like a very natural generalization of PINNs in the Bayesian framework. So the point is, we just like put Bayesian framework on the weight of the neural network. And first we set the prior on all the parameters, and we define the likelihood, and then we can get the posterior. Well, the posterior is like, although you have like unnormalized expression, but basically you need some sampling techniques to get the samples of the posterior, and then you can use samples to get the mean and standard deviation of the output. And as we can see that that's 3 key points: the prior, likelihood, and posterior. Likelihood is actually kind of easy. Here it is. So for example, still like we use a neural network to present U. I will use U tilde here as to denote the output of neural network, and then we can get like F and a boundary condition. Well, sometimes the boundary condition is like, it's not directly boundary, Newman boundary condition, etc. So I just write like here. Lambda is the parameter in the PDE, and you have the observations U, B, and F. I will use U bar, F bar, B bar to denote the observation. Well, we assume that the observation is the ground truth plus a Gaussian random noise. So the likelihood, well, so conditioned on theta, which is the parameter of the neural network, the probability of the probability of observing the data is going to be the product of observing the data on U and the product the data on F and data on B, and each term is going to be like a Gaussian, as we assume, because this is like a Gaussian noise, and so this is likelihood. And so the posterior will, as we say, PD, like this is like marginal likelihood, which is untrackable, because you have like a integral, but in essential we would have unnormalized posterior as P theta product P theta conditional D. The prior is given, so we have an analytical expression of this, and then you can use HMC or Bayesian invariance to sample this stuff. We'll discuss the prior later. So here I show the pseudocode of Monte Carlo, Hamiltonian Monte Carlo. I don't want to explain too much of this, because this is something like a very standard. And the only thing I want to mention is that basically in the Hamiltonian Monte Carlo, you also need a gradient with respect to the theta, which is parameter of neural network. But this is not a problem at all, because you can still use auto differentiation to get a gradient. So here we show the example of a forward problem, the Allen tau equation, which looks like this. And we consider like, we assume that we have 500 sensors for F, which are uniformly randomly distributed in the domain of like, this is a square domain. And in addition, we also have 25 equally distributed sensors at for U at each boundary. So here we also consider 2 different noise scale at all the measurements. So we assume that data the error is 0.01 and 0.1. Okay. And here they are. So we can see that Okay, the left part is the 1% noise, and the right hand side is 10% noise. So for the first case, we can see that like if you use HMC, we can see that the error is like 0.0, it's very small, I should say. And the standard deviation, we will see that the point is, firstly, the predictive means are close to the exact solution, or the error is very small. And secondly, the error are almost bounded by 2 standard deviations, are mostly. So basically, this means like the standard deviation is, the standard deviation just gives you the reasonable uncertainty. That is exactly what we want. And thirdly, so if we increase the noise from 1% to 10%, while the error like increases for maybe like 10 times, but the standard deviation also increases for 10 times. So which means, so basically like the uncertainty of standard deviation, uncertainty also increases as the noise scale increases in the data. So which means so we will conclude that the uncertainty given by standard deviation is totally reasonable. However, we want to mention that the variational inference is not as good as Hamiltonian counsel, because this is just like a bad result. So I will not introduce what is variational inference, because it's not recommended at all. If we use dropout, which is like another technique for uncertainty quantification in neural networks, it also didn't work in this kind of problem. So basically, I just want to conclude that HMC is like pretty recommended. As for the inverse problem, okay, so it's kind of similar to the forward problem, but you only need to also put a prior on K. So take this equation for example. Well, we don't know K, we want to infer K, but we know lambda. Okay, I think we have, okay, I didn't put here. So we assume that we have like 22 sensors for F, which are equidistant placed. And also we have a boundary condition. And apart from the boundary condition, another 6 sensors for U are placed in the interior of the domain to help identify K. We also assume that Gaussian noise are present for all the measurements. So, as always, as before, we consider like 1% error and 10% error noise. And we set the prior for the K as just standard Gaussian. And here are the results for the predicted K. The ground truth or exact value of K is 0.7, and we can see that well the BP with HMC still works very well. I mean, still the same observation. First, the mean is pretty close to the ground truth, and the error is bounded by 2 standard deviation. And as we increase the noise scale, the uncertainty of standard deviation also increases. So pretty reasonable. Well, I should say like the other 3 is not quite. I mean, this one variational events is not bad, but dropout it totally doesn't work. So this one is best. Anyway. It was mentioned that the accuracy of the prediction could be significantly reduced if the scale exactly doesn't match the prior. So just as all the Bayesian framework, the prior is super important. As an example, so we first rewrite this equation like this, and we set like K alpha still at 0.7, but the K itself could be like, for example, 50. So here we set like a K at the ground truth K as 50. Well, alpha is like small, so that K alpha is still 0.7. So basically, this is still the same equation. Okay. Then we compare the two kind of priors. The first prior is still as usual, like standard or normal. But as we can see that, well, this unburning is just like the steps in the HMC. Here I show that 2 just means that okay, we have converged. but even we have conversion, we'll see that the mean is far away from the ground truth, which is 50, and the standard deviation is actually pretty small. It didn't cover the area at all, so which means this is bad because it is bad prior. But in this case, actually, we can use we can use this prior like this. We set the log k as normal, which means k is like exponential of normal. And then we can get very good result. This is actually very good. This is actually very good prior for the problem where don't know the scale of k. For actually we compare we apply this prior for like another two problems. So first we set k as 100 or k as still at 0.7. We can see that in both problems that work very well. So we just conclude that like in problem where don't know the exact scale, you can use it. You can use the prior like this. And then this is like a 2D inverse problem on the diffusion reaction equation. And I think still we want to infer k. Okay, I think so. The ground truth of k is 0. I think it's 1. I think, yeah. And it's just like conclusion as before. So BP with HV still works very well. Okay. Then I want to show something interesting. So is the extrapolation of BPs. Here, so basically, why I care about this? Because in classic methods, usually you always need some, like for example, boundary condition, etc. But the extrapolation is something we care. For example, in this problem, we suppose we only have data of data u here, or 4 point. We don't have data on the right hand side, like the where x is positive. Well, and for the data of f, we still assume that we have a lot of data on f. Well, the left hand side is 1% noise, and right hand side is 10% noise. And we can see that even we don't have data of u here at all, it's still extrapolate very well, I should say. And here you can see that as we go like x go larger, will uncertainty also. I mean, while the error is like still kind of large, but uncertainty also become large. But I mean, the extrapolation is still like kind of good. This is something different from I mean vanilla neural networks. If you don't know the PDE, you can never extrapolate u as good as like this. The reason why it can do well is just because you have the physics informed here. Okay. And then it's just like a comparison with vanilla neural networks. So this is one. This one is a 1% error. This one is a 10% error. And the first row is for vanilla pins, and the second, I mean vanilla pins is just what I introduced in the first section. And the second row is the B pins with HMC. So in this problem, they both work well. There's no significant difference. But in this one, you can see that like vanilla pins totally failed in this, and also here is kind of bad. I didn't show I mean this is actually the inverse problem. So we want to infer k. I didn't put it here because anyway. Because I don't have space here. So, but the point is, in our paper, you can see that the inferred k is also very bad for vanilla pins, but very good for Bayesian pins. You can check our paper. That is because, so basically like the vanilla pins is not very robust if the data is noisy. Well, you can, of course you can like do some technique like regularization or like put penalty on the weight, but that is like essential kind of equivalent to Bayesian pins. Okay, we'll put the prior last because the prior of the neural network is actually a very very difficult problem, I should say. Honestly, okay, I've seen like a lot of papers discussing how to sample the posterior, and like there are like bunch of papers talking about like Hamiltonian MC, the stochastic Hamiltonian MC, and and also other versions of variational inference. Literally a lot of versions of variational inference. But I've seen few papers discussing the prior of B-pins. Well, okay. A common use prior for theta, the parameters, is just like we said, each component of theta is an independent Gaussian distribution with zero mean, and the entries of W and B, which has a weight and bias, have the variance sigma and like 2 sigma respectively. So they're totally independent. In this case, it can be shown that, this is interesting, it can be shown that the prior of the function is actually a Gaussian process. The Gaussian process just means like finite x, I mean finite u at, I should say u and finite x are Gaussian random variable, multi-dimensional variable. As the width of the infinite layer go to the infinite, but we fix the, I mean, of course we need to scale the sigma. So this is actually known for more than 30 years, I should say, maybe not exactly more than, but in 1990s we already know that. Actually, but even we know that this prior is a Gaussian process, it is still not trivial to optimize, or like to say how can we select, how can we set the variance sigma and sigma W and sigma B. It's not trivial at all. It's not trivial. And we also remark that due to the finite width of neural network, because this theoretical, this theory, like you say, okay, the width of the hidden layer goes to infinity. But in real world, real application, we only have finite width. So the point is the derivatives of U tilde could be far away from Gaussian processes, in contrast to the derivatives of Gaussian process, which are also Gaussian process. So this is actually unique for pins, because in pins we need to do the derivative. So for example, here we can see that, okay, this is like two hidden layers, each of width 50. 50 is not bad. And you can see that like the neural network itself is already very close to a Gaussian process. So the black line is the Gaussian fitting of the output density. So but the derivative is kind of not exactly a Gaussian process now, Gaussian now. And the second order derivative is even worse. So okay, so I should say that the prior for the derivative of neural network is still like under investigation. We didn't investigate that very deeply in the paper, but we'll do that in the future. And also, as I mentioned, how to set the prior is still, I think, is maybe the most important problem we need to do now. And well, actually, it's undergoing research now. Okay. Okay. Let me summarize. So the spirit is to employ two or more neural networks sharing the same parameter to represent functions, differentiations, etc., and such PDE. And we can solve the forward inverse problem in the same framework, especially good for problem with gappy data. It is also possible to tackle integration using, but by the way, it is also possible to tackle integration using quadrature or Monte Carlo. And secondly, we can employ pins in the Bayesian framework to tackle uncertainty right from the data. So that's it. And here, so basically the results are coming from this 3 paper. So the first two is like these two were the postdocs in our group, and this one, or these three, I should say. So this work joint work with Xuhui Meng and my advisor. So this paper is just like I think it's published online this month on JCP. Okay, Journal of Computational Physics. Yeah, that's all. Thank you. Any more questions?
Yeah. Quick question is fluid mechanics problems the primary like real world examples that you've used these pins on?
Yes. So okay, I didn't really do the real world problems. So in this paper, they are still using simulation data, but later, well, our group has applied this. So okay, so that problem is not part, so maybe I should not talk too much. So
Sure.
like you have like a cup, and this like you know the I don't know. So basically, you have like you have a camera taking photos on the top of the cup. I don't know how they do that. And basically, there you have like the from the cup from the photo you can get the density. I don't know how they do that. And then with this kind of observations, you apply pins, and then you can get the velocity field. That is actually very interesting. That is the real world stuff.
I know we lost some people after the hour, but unless there are any other questions, that was great. Really appreciate you coming in.
Yeah, I also really appreciated the talk. Thank you. I had one more question. So when you were introducing the Bayesian PINNs, you were talking about situations where you have the boundary conditions given by you, as well as some, you know, some measurements in the center of the domains. And in particular, there were a few slides later where you had very involved. Yeah, this one, for example. Back to.
Yeah, this one, right?
One more back, actually. So just the setup of the assumptions. Or one more.
You mean this one? So this is the inverse problem.
No, it was the inverse problem. So it was were these decisions were they motivated by something in particular? I noticed that there are different the errors are of various scales, and you have very particular. Like you assume F has a very small scale error, whereas things like B and U have a larger scale error.
Oh yes. So basically, we designed this problem just to say like U and F to be the same scale. But okay, if the problem you are tackling, you have different scale. You need to normalize it. Like you definitely need to put like all the terms in the same scale in the same scale. That is like because the neural network is just good at, for example, in the scale of 1. You cannot tackle, say, if the F is if the F, for example, the scale of F is like 1000 and the scale of U is like 1. It basically will just neglect U. Make sense? But I think this is not a big problem because you can always like modify. I mean, like to put parameters on your equation to make all the terms in the same scale, right?
Right, but when, like, for example, if you're training K and you're not sure what scale K is, so you use, say, the logarithmic prior. How does that?
Yeah, exactly. That's it. Yeah, you get the point.
I see. Okay, thank you.
Yeah.
Okay. Well, unless there's anything else, thank you very much, Liu.
Thank you. Thanks again for inviting me.
Yeah, of course. Really appreciate it. Have a good rest of your day, everyone, and take care.